Hi, in this video, I'm going to go through the AQA AS-level Chemistry paper. This is the 2020 paper, paper one. I'll just do the first half in this video and finish in a later one. Okay, so the first question about atomic structure, general trend for increase in ionization energy across period 3. Give one example of an element that deviates from this trend. Right, 3 marks. Well, there are 2 answers. You only need to give one of them, but I'll give both of them anyway. Right, you can have, let's see where the electron comes from then. So the first electron is coming from 3s there. That's from 3s. From aluminium, it's coming from 3p. Now that's a new subshell. Okay, so the first ionization energy of aluminium is slightly lower than magnesium's. And the reason for that is the electron is being removed from 3p, not 3s. So it's slightly further from the nucleus. And there's a bit more shielding. Okay, that's one you could have. Now, when you remove the silicon, it's coming from 3p, phosphorus 3p, and sulfur is from 3p. Now you get, as you go from aluminium, silicon, phosphorus, you get an increase as the nuclear charge increases, and it's coming from the same shell. But of course, with sulfur, there's a slight drop because the electron you're removing, right? This is the electron you're removing in the case of sulfur. Right, here's the 3p orbitals. Well, that's for phosphorus, but if it's sulfur, the electrons have to pair up. So you're removing this electron, which is paired up. So there is you get pairing of electrons in the 3p shell. So there is some repulsion. So the first ionization energy of sulfur will be slightly lower than that of phosphorus. That's a very standard question. They always ask that question. Not a very imaginative question. I think not many people did this paper, I don't think, and I don't think because of the pandemic, and I don't think they could really come up with any very original questions. Okay, give an equation including state symbols to represent the process occurs when the third ionization of sodium. So you're removing the third electron. So sodium's already lost 2 electrons, so it's the Na2 plus ion, and it's got to be a gas. And it's going to turn into Na3 plus. And that's a gas also, and an electron there. Okay, of course, the common wrong answer there would be somebody going from sodium to Na3 plus 3 electrons. That is the wrong answer. That is actually would be a combination of the first, second, and third ionization energies. That would be wrong. Okay. Okay, figure 1 shows the successive ionization energies of a period 3 element. Okay, and what you've got to do is the question says you've got to identify the element X. And okay, so you can see here that for the first electron, the second, the third, the fourth, and the fifth, there's just a modest increase in first in successive ionization energy, but for the 6th one, there is a big jump. Now that would indicate that you have got 5 electrons in the outer shell. And of course, the 6th one is much harder to remove because you're removing it from the next quantum shell in, a lot closer to the nucleus. So it's got 5 electrons out shell, so it must be in group 5. And if you look, it says the period 3 element, which is in group 5, that is phosphorus. Okay, so with the 3 marks, I would say 1 mark for saying there's a big jump between 5 and 6, 1 mark saying there must be 5 electrons in the outer shell, 1 mark for group 5, and that's phosphorus. Okay, titration now. Right, so, right, the student dissolves an unknown mass of sodium hydroxide in water to make 200 centimeters cubed of an aqueous solution. So I'm going to draw a little picture here. There is our 200 centimeters cubed of solution in a volumetric flask. Right, they pipette out 25 centimeters cubed of that. That's an eighth of it, isn't it? And they put that into a conical flask. And they titrate that against sulfuric acid. There's a burette. The concentration of the sulfuric acid they give us is 0.15 mole per decimeter cubed. Okay, now how much of that do we need? Well, we need to look at the titers here. Now, we only take concordant titers, so they've got to be within 0.1 of each other. So it's only those two that you should take. And the average of that will, of course, be 19.575 centimeters cubed. Okay, so now we've got to calculate the mass of sodium hydroxide. All right, so what we're going to do, first of all, I'm going to work out the moles of sulfuric acid because we've got the concentration and we've got the volume. Okay, so let's do that. Is equal to the concentration times the volume, 0.15 multiplied by 19.575 over 1,000, because the volume is going to be in dm cubed, of course. That gives us a number of moles of 2.936 times 10 to the minus 3. Right, now we need to deduce the number of moles of sodium hydroxide. Now we've got 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. So the moles of NaOH is going to be double that. That is equal to 5.875 times 10 to the minus 3. Okay, now that is in 25 centimeters cubed. But we want to find out how much we've got in 200 centimeters cubed. So look here, what we started off with, we had 200 centimeters cubed and we only took 25 out of that. So that's 25 out of that. We took 1/8 of the volume out there, didn't we? Okay, so the total number of moles we've got to multiply by 8. Okay, so let's do that. So the moles NaOH in 200 centimeters cubed is equal to 5.875 times 10 to the minus 3 multiplied by 8, which gives us 0.04698. Now we need to work out the mass of sodium hydroxide. So how do we do that? Well, mass NaOH is equal to moles times by the MR. Right, the MR of sodium hydroxide is 40. So the number of moles there is going to, so the mass is going to be equal to 0.04698 multiplied by 40, which is equal to 1.879 grams. We should really give that to 3 significant figures because all our data is given to 3 significant figures. So the final answer is 1.88 grams of NaOH. Okay, now some questions about titration here. Right, the student uses a funnel to fill a burette with the sulfuric acid After filling, the student forgets to remove the funnel from the top of the burette. Suggest why this may affect the titer volume recorded. Well, quite often, if you have the funnel, you have a drop of solution trapped between the funnel stem and the burette. And quite often what happens is halfway through the titration, that drop falls into the burette. So that means you are you're going to slightly underestimate the volume of acid that you've added. Okay. Right, fine. Right, an advantage of using a conical flask rather than the beaker for the titration, well, that's simply that it allows you to swirl it without spilling it, okay? Okay, right, now, question about time of flight spectroscopy. Right, define the term relative atomic mass. So that's a standard question that always exists, and you've got to know the definition for it. Okay, it is the mass of an average atom divided by the mass of an atom of carbon-12 multiplied by 12. There are several different definitions of that, but I find that one the easiest one. That's one I'd use. Okay, so krypton is ionized using electron impact, and the mass spectrum of the krypton has 4 peaks. Okay, so we've got the data shown here. Okay, we've got the MZ value and the relative intensity. Okay, now those relative intensities, usually they're in percent, but they're not here. They don't add up to 100. If you add up 6 plus 1 plus 28 plus 8, that comes to 43. Okay. So what we've got to do is, we've got to do 6 multiplied by 82. Let's see the mass of those, plus 1 times 83, plus 28 times 24, plus 8 times 86, sorry, 28 times 84, not 24. And divide by the total number 43 there. We've got to give it to 1 decimal place. If you do that on a calculator, you get an answer of 84.0697. We should give it to 1 decimal place, so that's going to be 84.1. Maybe give that a common sense check. Yeah, it should be about 84, because look, that's the most abundant one. Okay, so it seems about right. So if you get an answer which is like 60 or something, then you've obviously done something wrong. Okay. Now we've got to do a time of flight calculation. Okay. So they give us the kinetic energy of the ion. They give the equation for it here, which they usually give us. They give us the kinetic energy. There. They give us the time of flight there. And we've got to find out the distance of the flight tube. So first of all, we need to write down, so what our expression, kinetic energy is equal to half mv squared. And velocity, well, that's equal to distance, the length of the tube, divided by the time. So that means v squared is equal to d squared over t squared. That's the way I would do it, rather than involving square roots. Sometimes make a mistake doing that at this stage. So we substitute that in for our value of v squared. Then we're going to get kinetic energy is equal to a half m d squared over t squared. Now we need to find out the length of the tube, so I'm going to rearrange that to give us d squared. I'm not going to do d straight off, I'm just going to do d squared. So the first thing I'm going to do is going to times everything by 2 there, so I'm going to get 2 kinetic energy is equal to m d squared over t squared. Rearrange that to get d squared, we get, I'll do it over here actually, d squared is equal to 2 kinetic energy t squared over m, where m is the mass of one ion. So we need to find out m now before we put any numbers in. So let's calculate m. Okay, so m, the mass of one ion, is going to be equal to the mass of 1 mole divided by the Avogadro number, yeah. Right, now the stuff we've got in here is 84, okay? That's 84 divided by 6.022 times 10 to the 23. And that gives us 1.4679 times 10 to the minus 22 grams. Okay, but in this equation here, unusually for chemistry, we need to have our mass in kilograms, not in grams. So we've got to convert that to kilograms, but divide it by 1,000. So divided by 1,000, that's 1.4679 times 10 to the minus 24 kilograms. Okay, now we are ready to put all our numbers into this equation here. We've got all those numbers ready. So let's do that. So we get d squared is equal to 2. The kinetic energy, they tell us, is at 4.83 times 10 to the minus 16. T is 1.72 times 10 to the minus 5. That's squared. Okay, and we want that over the mass, which we just worked out from there, is 1.4679 times 10 to the minus 24 kilograms. So we get a value of d squared there is equal to 2.048. So now we want to find out d, take the square root of that. So that is equal to, the square root of that is 1.43, and the units are going to be meters. And that seems like a sensible answer for how long the tube would be. If because it's a piece of apparatus which fits into a room. So if you work out an answer like 1,400 meters, and obviously it's not going to fit into a room, so you've gone wrong somewhere there. Okay, so pretty straightforward, but lots of possibilities for making mistakes, really. So got to be careful with that sort of question. It's the same question they always ask for those time of flight things. So once you can do it, Okay. About enthalpy changes, state the meaning of the term enthalpy change. Okay, this is a question people often don't remember. So they don't remember what the right answer is. Enthalpy change, strictly speaking, is the energy change measured at constant pressure. People do forget that. It's kind of a bit of an obscure condition, really, isn't it? Okay, right. Okay, so this is a 6th marker about experimental technique here. Okay, so a student determines the enthalpy change for the reaction between calcium carbonate and hydrochloric acid. Right, there's mistakes in this method, okay, and we've got to talk about what they are. Okay, so explain how the experimental data, experiment method, and use of apparatus can be improved to provide more accurate data. Okay, and describe how this data can be used. So we'll do that second. That's the second bit. I'll do that in green. We could do that afterwards. First of all, let's look at these mistakes. Right. So this is a minor mistake, and a lot of people would use a measuring cylinder here. Okay, because you are going to get bigger errors. I would say, just for the sake of it, use a burette instead there, or a pipette. It's more accurate. A lot of people would use a measuring cylinder because all the heat losses involved in this mean that the sort of error introduced by a measuring cylinder is quite trivial anyway, but let's say that anyway. Right. Now this one, weighing out the solid. So again, they weigh out 2.5 grams. They really should. There could be a little bit left on the watch glass afterwards. So they should measure the mass of the empty watch glass and subtract it. To find the real mass added. Okay. Again, the amount of solid that you would get left there would be so small in this kind of, when you've got big errors with the heat loss, people probably wouldn't bother measuring by difference, but we'll say that anyway. Okay. Now the other mistake is kind of obvious. They're adding this into, they're using a glass beaker here, right, which is not a good insulator. You should use a polystyrene beaker. Instead of a glass, so that's a mistake. And then this next bit here, right? So stir the mixture with the thermometer, fine, and record the maximum temperature reached. Now, if you do that, you will underestimate the temperature rise. How should you do that? Now, you've probably done this. It's one of the required practicals, required practical 2, and they always ask this question. Actually, they always. So you shouldn't just measure the maximum temperature. What you should do is you should measure the temperature every minute for 3 minutes. Then you should add the solid in minute 4. And then you should continue to measure the temperature every minute for the next, say, 10 minutes. Okay, now explain. So we've got that. Now describe how this data can be used to determine an accurate value for the temperature change. Okay, right. So this is to find out delta T. Right. So what do we do with those results? Well, we plot a graph. Okay. You might want to draw a little sketch graph here. Plot a graph of temperature v time. Okay, so here's our graph. Temperature, and this is time in minutes. And you should plot, so there's okay, this is where you're going to add the solid. That's 4 minutes there. And the temperature is going to do something like this. It goes up, and then it starts dropping. okay? And it's dropping because it's cooling down. And what you should do is now you should extrapolate two lines. You should extrapolate that one forward, that one backwards, and you would estimate delta T to be there, okay? So, and in doing that, look, you will you take into account that the fact that the solution is losing heat all the time to the surroundings, and you adjust it for that. Okay, so I think you're going to get your 6 marks for saying all that, and I would probably draw a little sketch graph and explain it that way. It's probably the easiest way of doing it. And that question has come up loads of times, and it is a required practical too, I think. Okay. And when it's come up in the past, people know that you should do that, but they haven't really interpreted the question. They don't quite crack on that that's what they're asking. Okay, now here's in a different experiment. We are adding hydrochloric acid to sodium hydroxide, and we want to find out the final temperature. We want to find out the final temperature. Okay, so how are we going to do that? Well, we need to use two equations. We need to use Q is equal to mc delta T, where Q is the quantity of heat released in the experiment, M is the mass of the solution, C is the specific heat capacity, and delta T obviously is that. And then we want delta H, well, that is equal to Q divided by the number of moles, I'll call that N, reacted. Right, let's combine those two things together. We're going to get delta H is equal to mc delta T divided by the number of moles. Now we were interested in delta T there, so I'm going to rearrange that to get delta T. So delta T is going to be equal to right, it's mc, sorry, moles, delta H divided by the heat capacity, specific heat capacity, and the mass mc. Okay. Now we need to work out N, the number of moles reacted. So let's do that. So N. Well, let's take the moles of sodium hydroxide there. So moles of NaOH, that's going to be equal to, well, how will we work that out? We know we've got 50 centimeters cubed concentration here, there, times the volume. Let's do that. So we've got 0.5 concentration times volume. So that's going to be 0.5 multiplied by the volume, 50 over 1,000. And that is equal to 0.025 moles. Now let's just check that all of that is going to react. Is all of that sodium hydroxide going to react? Have we got enough hydrochloric acid to react with all that? Well, we have, because if you look at the hydrochloric acid, look, we've got the same volume and the same concentration of hydrochloric acid. And they react in a 1-to-1 in that equation there. So yeah, the number of moles of sodium hydroxide or hydrochloric acid that's going to react is 0.025. So what we're going to do is put our numbers now into this equation here. Let's do that to find out delta T. So delta T, oh no, but before we do that, let's just talk about M. The total M is the mass of the solution. Well, we're adding 50 centimeters cubed to 50 centimeters cubed. So the total volume is 100 centimeters cubed. And they tell us the density is 1 gram. That's just density of water. So that the mass is going to be equal to 100 grams here. I just say one more thing about specific heat capacity here. We're going to have to be careful with that because that's measured in joules per gram. Yeah, joules, not kilojoules. So what I'm going to do with my delta H here is I'm going to have to convert my delta H into joules. So I've got to times that by 1,000. So that's going to be equal to 57,100 joules. Okay. So I haven't done that. We've got all those numbers together now. Let's put them into here. So delta T is equal to moles 0.025 multiplied by 57,100 divided by the mass of the solution, which is 100, and the specific heat capacity of the water, which is 4.18 joules per gram per Kelvin. Right, do that. We get a value of 3.41 degrees C, so a pretty small temperature rise there. Now we need to find out the final temperature. So the final temperature then is going to be equal to the initial temperature, which they tell us was 18 degrees C. Sorry, was it 18.5 degrees C? Plus the temperature rise, which is 3.41. So the final temperature is going to be then 21.9 degrees C. Okay. Now, when I first did this calculation, I thought I'd gone wrong somewhere because this is like obviously a pretty small temperature rise, and that wouldn't be a great experimental design because you're going to get a big percentage error with your thermometer, and they lead you into the next. That is the right answer. They lead that into the next question now, I think. Okay. So suggest how, without changing the apparatus, the experiment could be improved to reduce the percentage uncertainty in the temperature change. Yeah, the temperature change is going to be big because the delta T is only 3.41, maximum 3.4, and your thermometer at most is going to be accurate plus or minus 0.1 degrees C. So you've got a big error involved there. Well, how could you make delta T bigger? Well, you can't use more solution. You want to react more moles, but you can't use more solution because that means you've got more water to heat up. So what you need to use use more concentrated HCl and then AOH. Okay, so if you double the concentration there, you're going to get double delta T. Triple it, which you could probably get away with that. Yeah, you're going to. So if they're using quite dilute solutions, I think this concentration of the solution was 0.5 moles per decimeter cubed. You can make that stronger. Okay, on to group 2 now. Explain why the melting point of magnesium is higher than the melting point of sodium. Right, so they're both metallic lattices, aren't they? But what we're going to say is the magnesium ion is, well, it's more highly charged, and it's also smaller than the sodium ion. Okay, so that means it's got a higher charge density. So that means the attraction for the ions to the delocalized electrons is going to be stronger. And that, of course, is what holds a metallic lattice together. So the attraction of the positive ions to the negatively charged delocalized electrons. So if you make that interaction stronger, you are going to get a higher melting point. You might also want to mention that there's more delocalized electrons in magnesium because each magnesium is losing 2 electrons, whereas in sodium, each sodium is only losing 1. Because it's an Na plus ion. Okay, more than enough there for 2 marks, I think. Right. Equation to show how magnesium is used as the reducing agent in the extraction of titanium. Okay, so this is a bit of recall here. You need to know that you extract titanium from titanium chloride with magnesium. You get a displacement reaction, magnesium more reactive, so you get magnesium chloride, which of course has the formula MgCl2, and you get titanium metal. Now we need to balance that with a 2 there. Right, okay, so explain it in terms of oxidation states, why magnesium is the reducing agent. Well, let's look at the oxidation state of magnesium here. It is 0, okay. Here it's an Mg2 plus ion. So it's got an oxidation number of +2. So its oxidation state, its oxidation number has increased. So the magnesium has been oxidized. Now that means it must be the reducing agent. Oxidizing agents get reduced when they react. Alternatively, you could explain that by saying, look, the oxidation state of titanium there, well, chlorine is going to be -1 oxidation state. That's +4 oxidation state there. And here it is 0 oxidation number. So the titanium has been reduced. What's reduced is the magnesium. So you could explain it that way. Right. Right, so precipitation reactions here now. State what is observed when dilute sodium hydroxide is that it's separate solutions of magnesium chloride and barium chloride. Okay, so if you remember you have to remember the trend in solubilities of the group 2 hydroxide. So starting off with magnesium hydroxide, calcium hydroxide, strontium going down group 2, strontium hydroxide, and barium hydroxide. Now the solubility increases as you go down the group. Remember that magnesium hydroxide is very insoluble. Calcium hydroxide is sparingly soluble. That's what lime water is, a solution of calcium hydroxide solution. And you can only make it about like 0.1 mole per decimeter cube. You can't make it any stronger than that because it won't dissolve very well. But barium hydroxide is pretty soluble. Strontium hydroxide is also pretty soluble. So state what is observed. Now, all you have to do is state. You don't have to do any explaining like I've done there. So you don't go on about that. So, but I am explaining. What will you get with magnesium chloride? You get a white precipitate. And you don't have to say what that white precipitate is. You just have to say you get it. And with barium chloride, with the white precipitate is actually magnesium hydroxide, of course. And with barium hydroxide, no visible change. You're not going to get a precipitation reaction because when you add the OH minus ions, yeah, they aren't going to form precipitate with barium because barium hydroxide is soluble. All right, shapes of molecules question. Okay, draw the shape of NCl3 and NCl4 plus. Okay, right, now before I draw the shape, I'm going to draw a dot cross diagram, which I think you should draw, but cross it out because that's not what they want in the answer. Remember, nitrogen is in group 5, so let's draw NCl3. Right, okay, so what do we get? We have a dot and from the nitrogen across from the chlorine, dot from the nitrogen across from the chlorine, dot from the nitrogen across from the chlorine. Nitrogen, of course, is in group 5. So it's got 5 electrons in its outer shell. I've only drawn 3 dots, so it has got another pair. It's got a lone pair there, okay? Right, so shape of NCl3 then, this is going to have, it's got Right, name the shape of NCl3. That's what we've got to do here. Okay. So I'll draw the NCl3. So you're going to have, right, this is going to be, it's going to be tetrahedral basically. Okay, but you've got one hydrogen coming towards you, one going back into the plane of the paper, one in the plane of the paper, and then you can have a lone pair here. Okay. It doesn't ask the bond angle there. So what would you call that? You call it trigonal pyramidal. Actually, I've drawn these as H's. Ammonia, they're actually chlorines, aren't they? Makes no difference. And also what I should do in my dot cross diagram there, I should put in all the chlorines electrons. So each chlorine is going to have 6 more because that's in group 7. So I'll just draw it for one of them. Okay, and the same for all those chlorines. Don't worry about them. So it's trigonal pyramidal. It's not asking the bond angle. Of course, that would be not 109.5 because the lone pair causes more repulsion. It's going to be 107.5, something like that. Right, let's do the shape of NCl4 now. Okay, so again, I'm going to draw a dot cross diagram. Right, so I'll do it in different color here. So we're going to have nitrogen, 4 chlorines around at this time. Right, we're going to have single bonds here, so dot and a cross, dot and a cross, dot and a cross, dot and a cross. I'm not going to draw my chlorines electrons there. But each one's got 7. There's your nitrogen. As I said, nitrogen is in group 5, so it should have 5 electrons, but it's positively charged, so it's missing 1 electron. So it's only got 4, and you can see I've only got 4, already got 4 electrons there. So if there's no other electrons, no lone pairs. So what we got there, we have got 4 bonding pairs. And so what is the bond angle going to be there? What kind of shape are we going to get? We are going to get, it's going to be tetrahedral, like methane. So you've got 4 chlorines there, that one in the plane, that one going into the paper. And another one here. Okay, so you've got, what's the bond angle going to be? Well, it's going to be 109.5. Why is it going to be that? Well, all the 4 bonding pairs are going to repel each other as much as possible, and that is how they can get as far away from each other as possible by forming that tetrahedral shape there. Okay. Right. Group 7 elements and their compounds. Chlorine is used to treat water even though it's toxic to humans. One reason why it's treated with chlorine, right, to kill microbes. Okay, and why is it okay to add it even though it's toxic? Because it is in, I'll probably say, in low concentration. And also what happens to it, it will, by the time it gets to the supplier, to the consumer, the water will have, the chlorine will have evaporated. Okay, an equation for the reaction of chlorine with cold water. So this is a straightforward recall. If you get chlorine and you react it with water, you get actually a disproportionation reaction happening. You get hydrochloric acid, HCl, and you get hypochlorous or chloric 1 acid, which is HOCl. Right, that is the reaction there. And it's a disproportionation reaction. They don't actually, but of course that's oxidation 0 there. Oxidation number -1 there for the chlorine, and here it's oxidation number of +1. So the chlorine simultaneously oxidizes and reduces itself. Okay, and more questions on group 7 now. Okay, so solid sodium iodide reacts with concentrated sulfuric acid to form iodine and sulfur. Okay, so yeah, these series of reactions of the solid halides with conc sulfuric acid, and you get a redox reaction. The iodine, the iodide is oxidized to iodine, and the sulfur and the sulfuric acid can be reduced to several things, including sulfur. So let's do iodide to iodine first of all. This one here, which is the easiest one. So we're going to have I minus, and that's going to go to I2. Right, we need to balance that, so we need 2 iodines there, and we're going to make 2 electrons, and we need 2 electrons on either side to balance the charges. Okay, so that's that one. First half equation. Let's do the next one. Conversion of sulfuric acid to sulfur. Okay, so we're going to have H2SO4 and that's going to get reduced to sulfur. Right, first of all, we need to balance for our oxygens. We've got 4 on the left and we've got none on the right. So we need to put 4, balance it with water. So we want 4 H2O on the right-hand side. Now we need to balance for hydrogens. Well, we've got here, we've got 8 hydrogens on the right and we haven't got any on the left. So we need 8 protons. Oh, we've got 2 on the right, sorry. So we need 6 H plus. Now we need to balance for charges. On the right-hand side of the equation, we've got no charge. On the left, we've got 6 positives coming from the hydrogens here. So that means we need to balance them by putting 6 electrons in, 6 negative electrons, 6 E minus. Okay, now we've got to do the final thing. We've got to give an overall equation for this redox reaction. Okay, now we need to balance the number of electrons. So we need to multiply this one by 3 because this is only 2 electrons. Well, this one is a 6 electron process. Okay, so we're going to get 6 I minus plus sulfuric acid plus 6 protons that's going to give us 3 I2s, 1 sulfur and 4 H2Os. There's our balanced equation. Finally, this question here now, it says identify one of the sulfur containing reduction product form when sodium iodide reacts to conc sulfuric. So we don't just get sulfur, you can reduce the sulfuric acid with iodide, can reduce it. Right, so starting off with the sulfuric acid there. Which in the sulfur there's got a +6 oxidation state. Well, it can reduce it to sulfur dioxide, which has got a +4 oxidation state. It can reduce it to sulfur, as we've seen there in that, which is 0. And it can also reduce it right the way down to hydrogen sulfide, which has got an oxidation number of -2. Okay, right. So you obviously can't include that one as an answer because that was said besides sulfur. So sulfur dioxide or hydrogen sulfide. Right, calculation now. Right, a student completes an experiment to determine the percentage by mass of sodium chloride in a mixture of sodium chloride and sodium iodide. Okay, So they dissolve it in water and they add silver nitrate solution. So what's going to happen there, you're going to precipitate out the chloride ions as that, and the iodide ions as silver iodide. And then they wash in dilute ammonia. Dilute ammonia will dissolve silver chloride, but it won't dissolve silver iodide. So you're going to end up with solid silver iodide here. And the mass of it is that much. Right. Why? So silver nitrate is added to the solution. Why is an excess used? Because, well, you want to make sure, you want to ensure that all the halide ions and I minus are precipitated out. You don't want any of them left in solution. Okay. Right. Now, calculate the moles in moles of silver iodide obtained. So that's pretty straightforward. So the moles of silver iodide is simply mass over mR. And they've given us in milligrams here, and they always have one of these. What's that in grams? It's 0.315 grams divided by 1,000. So that's going to be 0.315 divided by the mR, which they give us here, is 234.8. And that is going to give us the number of moles, 1.34 times 10 to the minus 3. Okay. All right, the next part, we're going to use that in the next bit. Right, it says now we've got to use that to work out the percentage by mass of sodium chloride in the mixture. Okay, so and they tell us the MR. A bit smaller. Right, they tell us the MR of so what we're going to say there. So right, 1 mole of sodium iodide or silver iodide, sorry, well, that came from 1 mole of sodium iodide. Okay, so then we can say there, what's the moles of sodium iodide in the mixture then? Well, that's the same with the moles of silver iodide, and that was equal to 1.34 times 10 to the minus 3. So now we need to work out the mass of sodium iodide. Do that. That's equal to the moles times by the MR. The moles we've got is 1.34 times 10 to the minus 3 multiplied by the MR. The MR of sodium iodide is 149.9. Right, what's that equal to then? That is equal to 0.201 grams. Right, it's asking us the percentage by mass of sodium chloride in the mixture. Right, what was the mass of the original mixture? The total mass of the original? Well, that was 600 milligrams. Okay, 600 milligrams, which is equal to 0.6 grams. Okay, so what's going to be our mass of of chloride, then we just got to subtract that. So that's going to be 0.6 minus the iodide, which is 0.0201. Okay, and that's equal to 0.399, okay, grams. So now we have to work out the percentage of sodium chloride there. It's going to be equal to the mass of it, 0.399, over the total mass of solid, which was 0.6 grams, times 100. That is equal to 66.5%. The pen is going funny there. Okay, that's our final answer. Okay, now I think that is as far as I'm going to go with that paper, and I will continue with that paper in the next video. Oh, it's raining